Hello everyone, welcome to this presentation. Today we are going to explore 5 fundamental semiconductor concepts: bandgap formation, the mass action law, p-type and n-type semiconductors, p-n junction operation, and breakdown mechanisms, including avalanche and Zener effects. By the end, you will understand how these concepts explain the electrical behavior of diodes and related devices. First, let's talk about band formation. An isolated atom has discrete energy levels. When two identical atoms are brought together, each discrete level splits into two because of wave function overlap. For in-phase combination, the symmetry wave function is obtained and has lower energy level. But for out-of-phase combination, the antisymmetry is obtained and has a node between nuclei and energy level is then higher. As the number of atoms n becomes very large, a crystal, this split level form a quasi-continuous set of levels and energy band. The lower band formed from bonding orbital is the valence band. Top energy is EV. The higher anti-bonding band is the conduction band. Bottom energy is EC. The band gap is the energy difference between the conduction band minimum and valence band maximum, which is from this equation, Eg equals to Ec minus Ev. If the Fermi level Ev lies inside a band as in metals, there are available empty states arbitrarily close to the electrons. Electrons accelerate under a field and conduction is high. If Ev lies in the gap, as in semiconductors or insulators, conduction requires exciting electrons accord Eg. At 0 Kelvin, the probability of finding electron at some energy E less than Fermi energy is 1, and the probability of finding electron at some energy E more than Fermi energy is 0. Next, conductivity. The conductivity is given by this equation, where Q is electron charge, N is electron concentration, P is hole concentration, and mu N are electron and hole mobilities. The current density can be written as this equation on the left box. So the conductivity is the proportionality factor between J and E. Metals have a very large free carrier concentration N, so the conductivity is very large. Semiconductors have smaller N and P, controllable by temperature and doping. The conduction in intrinsic semiconductors. When we apply an electric field across a semiconductor, the energy bands bend. Electrons in the conduction band move opposite to the field, while holes in the valence band move in the same direction as the field. This means both electron and holes contribute to current flow. The total current density can be written as J equals to sigma times E, where sigma depends on the electron and hole concentration and their mobilities. Let's talk about electron and hole concentration. The number of electrons and holes depends on the density of states, the Fermi Dirac probability, and the energy levels for electrons in the conduction band. The concentration can be expressed as Nc times E to the power of minus Ec minus Ef over kT. Here Nc is the effective density of states, which depends on temperature. So as temperature increases, more carriers are generated, and conductivity increases. To derive the mass action law in P equals to Ni squared, start with the true expressions, which is the expression of electron concentration and hole concentration. Multiply them together, we got the next equation, and then we recognize that the band gap energy is Eg equals to Ec minus Ev, so we can define the intrinsic concentration square as Ni squared. Therefore, the mass action law is Np equals to Ni squared. As a result, from the calculation, we assume that this derivation uses thermal equilibrium and the Boltzmann approximation. Next, let's talk about N-type semiconductor. N-type is added donor impurity atoms, for example, group 5 in silicon. Donor levels lie just below EC at room temperature. These donors are usually ionized and contribute free electrons to the conduction band. The majority carriers are electrons, so N is larger than P. The Fermi energy moves upward toward the conduction band. The another type is p-type semiconductor. P-type is added by acceptor impurities, for example, group 3. Acceptors level lie just above EV. Acceptors capture electrons from the valence band, leaving mobile hosts the majority carriers and are hosts, so P larger than N. The Fermi level moves downward toward the valence band. The difference between majority carrier and minority carrier is that majority carrier is the dopant supplied carrier, electrons for N-type, and host for P-type. Minority carrier, the other type, important for diffusion and recombination processes. Let's talk about p-n junction formation and equilibrium. Starting by taking a p-type region and n-type region, each at thermal equilibrium but with different Fermi levels. When they touch, carrier diffuse, electron diffuse from N into P, host diffuse from P into N. When carriers diffuse and recombine, they leave behind charged, immobile ions, ionized donor, which is positive charge in the N side, and ionized acceptor, which is negative charge in the P side. This region depleted of mobile carriers is called the depletion region. Those fixed charges set an electric field that oppose further diffusion. Equilibrium is reached when the built-in electric field prevents net charge flow and a single Fermi energy exists throughout the structure. In the band diagram, this equilibrium appears as band bending. The conduction and valence bands bend so that the Fermi energy is flat across the junction. Next, we will talk about p-n junction under different biases. First, p-n junction at equilibrium, which is no bias. When no external bias is applied, the p-n junction is in equilibrium. Electrons from the inside have diffused into the p side and recombined with hosts. Hosts from the p side have diffused into the n side and recombined with electrons. This diffusion process leaves behind immobile ionized donors and acceptor, creating the depletion region. Inside the depletion region, an electric field exists that drives carriers in the opposite direction to diffusion. As a result, diff current balance diffusion current. At equilibrium, the total current across the junction is exactly zero. Even though individual diffusion and drift component flow, they cancel each other. The energy band diagram shows this balance clearly. The band bends and the Fermi energy level becomes flat across the junction. This indicates equilibrium, no net current flow. p-n junction under forward bias. Apply a forward voltage V positive on P relative to N. The applied bias reduces the built-in barrier by V. In the band diagram, the band bending is reduced and the effective barrier for carrier injection decreases. As a result, electrons in the N side more easily cross into the P side and hosts cross into the N side. These injected minority carriers diffuse away from the junction and recombine in the quasi-neutral regions. This diffusion current is the dominant component of the diode forward current. This means for small forward voltage, the current can increase exponentially. Next, p-n junction under reverse bias. First, apply reverse bias positive on N relative to P. The barrier increases and bands bend more. The depletion region widens and the electric field in it strengthens. Mobile carrier injection is suppressed and only a small reverse saturation current (IS) flows due to thermal-generated minority carriers. At sufficiently large reverse voltages, the diode may undergo breakdown, a sharp rise in a reverse current two main breakdown mechanisms exist: Zener tunneling and avalanche impact ionization. Which mechanism dominates depends mainly on doping and field strength. Breakdown mechanisms. There are two types. First type is called avalanche. In more lightly doped junctions, the space charge layer (SCL) is wider. Under strong reverse bias, carriers that exit, thermal-generated or injected, are accelerated across the wide SCL and can gain enough kinetic energy to ionize lattice atoms on collision, create new electron-hole pairs. This impact ionization. The newly created carriers are themselves accelerated and create more pairs, leading to an avalanche multiplication of carriers. The device current increases rapidly when the field exceeds a critical value. Avalanche breakdown usually occurs at higher reverse voltage, more than 6 volts, and the breakdown voltage increases with temperature. The another one is Zener tunneling. In heavily doped junctions, the depletion width is very narrow, and for a given reverse voltage, the electric field can be enormous. Under strong field, electrons at the top of the valence band on the p side can quantum mechanically tunnel directly into empty conduction band states on the inside. This direct tunneling creates carriers and a sudden reverse current. The Zener effect, it typically appears at low reverse voltages, often less than 5 to 6 volts, depending on doping. Because tunneling probability increases when the bandgap narrows with temperature, Zener breakdown voltage usually decreases with temperature, negative temperature coefficient. Thank you for listening.